So, in the ninth module of chapter 9, we shall try to prove the Gauss-Bonnet theorem, which was stated in module 8, and here we shall see some applications of Gauss-Bonnet theorem also. We know that two surfaces are topologically equivalent if they have one-to-one continuous correspondence. We shall see that if a surface is topologically equivalent to a sphere, then the integral curvature, that means the double integration with k dA, which we have obtained in our module 8, the integral curvature is of value 4 pi, and if a surface is topologically equivalent to a torus of genus 1, then its integral curvature is 0. So, that means the Gauss-Bonnet theorem is applied to find the integral curvature of a surface. So, let us see the proof of the Gauss-Bonnet theorem with some applications. Name of the module 9 of chapter 9 is Gauss-Bonnet theorem with some applications continued. So, here we shall see the proof of Gauss-Bonnet theorem, and secondly some applications of Gauss-Bonnet theorem. Now, to prove the Gauss-Bonnet theorem, let gamma s, that is U s and V s, be the curve according to proposition 9.32, and then we have the geodesic curvature of the arcs of this gamma is equal to 1 by 2 root A11 A22, and within the second bracket del A22 by del u dV ds minus del A11 del v du ds plus d alpha I ds. We have obtained this result or expression from proposition 9.32, where alpha is the positive angle from R u to gamma dash s within the interval S I and S I plus 1. Now, by integrating this equation and summing, we have this expression, a summation I equal to 0 to m integration S I to S I plus 1 kappa g s ds equals to summation I equal to 0 to m S I to S I plus 1 by 2 root A11 A22, and within the second bracket del U22 by del u dV ds minus del A11 del v du ds and whole ds plus summation I equal to 0 to m integration S I to S I plus 1 d alpha I ds ds. Now, from Green's theorem on UV plane, we know if f and h are two differentiable functions of u and v in a simple region R, whose boundary is given by the curve C u s v s, or we can take this one as gamma also, then it follows this expression I equal to 0 to m integration S I S I plus 1 within the first bracket f du ds plus h dV ds whole ds equals to double integration within the region R del h del u minus del f del v within the first bracket du dV. So, this expression gives us the statement for Green's theorem, and we know that the Green's theorem gives us the relation between the line integration and the double integration. So, by this relation, the 30 equation number 30 reduces to this expression I equal to 0 to m Si to Si plus 1, integration is between Si to Si plus 1, kappa gs ds is coming to this one. Double integration r within the bracket del del v within the second bracket 1 by 2 root a11 a22 del a11 del v second bracket close minus del del u again within the bracket second bracket 1 by 2 root a11 a22 del a22 del u second bracket close du dv plus I equal to 0 to m integration Si to Si plus 1 d alpha I ds ds. So, this relation is due to the Green's theorem. Now, since curvilinear coordinate system is orthogonal, we have a12 equals to 0, and so Gaussian curvature is k equals to minus 1 by root a within the bracket this expression. And again the double integration k dA over the region R is actually dA means this expression root a11 a22 minus a12 square du dv, that is actually k root a du dv. So, using 32 and 33, 31 becomes this summation I equals to 0 to m integration Si to Si plus 1 kappa g s ds equals to minus double integration r k dA plus summation I equal to 0 to m integration Si to Si plus 1 d alpha I ds ds. And again by proposition 9.33, that means the proposition for turning tangents given in the module 8, we have this one summation I equal to 0 to m integration Si to Si plus 1 d alpha I ds ds have this expression summation I equal to 0 to m alpha I Si plus 1 minus alpha I Si equals to plus minus 2 pi minus summation I equal to 0 to m theta I. Now, since the gamma s is positively oriented, we have stated in our theorem that gamma s is positively oriented, the sign will be considered plus. Thus, the summation I equal to 0 to m integration Si Si plus 1 kappa g s ds plus double integration over the region R k dA plus summation I equal to 0 to m theta I equals to 2 pi, and hence the theorem follows. So, as the gamma s is positively oriented, so we are not taking the minus sign, we are taking the plus sign only. So, this is the proof of the Gauss-Bonnet theorem. Now, this theorem can be proved if the coordinate curves are not orthogonal by using conformal mapping, but we have not included it here. just now we have seen the proof of Gauss-Bonnet theorem. In this proof we have considered the curvilinear coordinate system on a surface is orthogonal, but the proof can be also done if the curvilinear coordinate system are not orthogonal. In the next section, we shall see some applications of Gauss-Bonnet theorem for different surfaces. Just we have mentioned that two surfaces are topologically equivalent if they have one-to-one correspondence, continuous correspondence, and if two surfaces are topologically equivalent, then one surface can be deformed in the process. So, here we shall find the integral curvature for different surfaces in this next section. So, in this section we shall see some applications of Gauss-Bonnet theorem. Before going to some applications, we just see the note here also that if gamma, that means the curve, consists of A marks of smooth curves making exterior angles theta 1, theta 2, theta m at the vertices, say rho 1, rho 2, rho m, where the arcs meet, then d alpha I measures only the changes of theta along the smooth curves. When we measure the kappa g ds over the gamma and not the jumps at the vertices, and the total change in theta along gamma is still 2 pi. So, actually this is the main portion what we have obtained in Gauss-Bonnet theorem, and this one can be visualized by the picture given in our previous module. So, there are A marks S1, S2, Sm arcs consists gamma, and they are making exterior angles theta 1, theta 2, theta m at the different vertices rho 1, rho 2, rho m. Then we have seen the total change in theta along gamma is 2 pi. And this one I have just mentioned also that this double integration over the surface or the region k dA is called integral curvature or total curvature or curvature integra is given by Gauss. So, this double integration is very important concept for surface geometry, and this double integration k dA is called the integral curvature. Now, just we have mentioned that a surface which has one-to-one continuous correspondence with the sphere is called topologically equivalent to the sphere. So, such surfaces can be obtained by continuous deformation of a sphere without breaking it. So, if we consider a sphere and if it is elastic type, and if we just press this sphere, it will deform without breaking it, then that surfaces are topologically equivalent to sphere, and that surface can be separated into two simply connected portions or regions R 1 and R 2 by a closed smooth curve gamma without any double points. That means, without any crossing, we can break or we can consider that surface into two portions R 1 and R 2. See, this is the figure. So, if a sphere is compressed and it takes in this form, then we can consider the two regions R 1 and R 2 and separated by the curve gamma, and the orientations are given along the directions. So, this surface is topologically equivalent to a sphere, and now we shall try to find the integral curvature of this surface by using Gauss-Bonnet theorem. Now, if we apply Gauss-Bonnet theorem taking gamma as boundary of R 1 first and then boundary of region R 2 with direction in such a way so that excluded region stays on the left side, we are considering the orientation in this way, then we have kappa g ds plus double integration R 1 k dA equals to 2 pi. So, this is the expression obtained from Gauss-Bonnet theorem, where kappa g ds is integrated along the curve gamma in one direction for the region R 1, and same kappa g ds gamma in the opposite direction, and the double integration is R 2 k dA, it is also giving 2 pi, but as this one has the opposite direction. So, this kappa g ds gamma has a negative implication, and so if we sum these two, so adding these two equations, we have the integration S k ds or k dA equals to 4 pi. So, adding these two results, we are getting this expression. Thus, the integral curvature of a surface which is topologically equivalent to a sphere is 4 pi. So, this is the value of the integral curvature of a surface which is topologically equivalent to a sphere. Next, we see another interesting surface, torus, which is a surface of genus 1, and the intrinsic geometry of torus has been taught in our earlier modules. So, if a surface S is topologically equivalent to a torus, then it can be changed into a simply connected region R by two cuts, and these cuts make the region R bounded by 4 smooth curves intersecting at pi by 2. So, we can make the surface into a simply connected region R by two cuts, and these cuts make the region R bounded by 4 smooth curves intersecting orthogonally. Then if we apply Gauss-Bonnet theorem along boundary, we have this one, because here the angles are making pi by 2. So, 4 angles is giving 4 into pi by 2. So, integration gamma kappa g ds plus double integration r k dA equal to 2 pi minus 4 into pi by 2, that means it comes to 0. Now, the integral of the geodesic curvature vanishes for this type of surfaces, and so k dA, the double integration k dA equals to 0. That means, the integral curvature of a surface which is topologically equivalent to a torus is 0. So, this is another interesting observation which we are getting from Gauss-Bonnet theorem. Now, the above two results can be generalized to any closed orientable surfaces of genus R. We know that a surface with holes, for R holes it is of genus R. So, we can state that any closed orientable surface of genus R has the integral curvature double integration S k dA equal to 4 pi within the bracket 1 minus R. It can be proved, but we have not included the proof here, but the result is very important, that the integral curvature of a surface, of a closed orientable surface of genus R has the integral curvature this one, 4 pi within the bracket 1 minus R. So, from this result, the previous two observations are coming easily. That is, for a sphere R equals to 0, because sphere is a surface of genus 0, because it has no hole, and so putting the value of R, we get the integral curvature is equal to 4 pi. And for torus, we know it is of genus 1, for one hole it is of only one hole, if we consider the torus of genus 1. In that case, the value is coming for integral curvature is 0, pi 1 minus, in the place of R we are putting 1, so it is 0. So, from this result, the above observations, the previous two observations are coming directly. So, for this one, this is the figure of a torus of genus 1, there is one hole and the integral curvature for this torus is 0. In the last module of chapter 9, that is in the 9th module, we have proved Gauss-Bonnet theorem, which is a very important theorem in the field of differential geometry. Here we have also obtained some applications of Gauss-Bonnet theorem. That means, we have obtained the integral curvatures of different surfaces which are topologically equivalent to a sphere or torus like this. So, with all these things, we end this module and also we end chapter 9.